Hello, everyone. In this session, we are going to talk about demystifying decentralized FAIR models for federated learning. My name is Subarna. I'm a manager data science here at Publicis Sapient, and I have Sharmistha with me. She's a senior manager data science at Sapient as well. So in this session, we are going to talk a lot about FAIR models and federated learning. And also, just one side note that if you have any questions, you can just ping us in chat and we'll take those questions during the session. Thank you. So in the next slide, we are going to talk about the agenda, and the agenda looks like this. We will be starting with a brief introduction about federated learning and how it works. Then we'll be talking about fair clustering, what is fair clustering and how we can incorporate fair clustering in federated learning. And lastly, we'll be talking about the architectures that go behind federated learning and how you can leverage them. And finally, we have the appendix section. So let's dive in. And the first thing is we wanted to let this know that what are the things that you can do to learn more about federated learning and where will you be, right? So in the next week, I think you will be able to identify those applications which are actually using federated learning. There are many applications. And in the first 3 months, you'll be able to understand properly what are the different phases of federated learning, how you can increase the privacy and security as you go with those phases. And by the end of 6 months, hopefully you will be able to create your own federated learning system where you will be able to do your machine learning task. So before moving forward in this section, I have two questions for the audience. I just want you guys to think about it. The first question is, are the company's data safe? Right. So, and the obvious answer is probably no, because we have so many instances where we see that people are, there's data breach happening, like the Facebook case. Even recently, there was a Facebook data breach happened where Facebook had to pay a lot of fine. So, apart from that, we have so many big names who are not able to protect their customers' data, like British Airways or Uber. Even the WhatsApp case is quite interesting, where they notified the users that they will be not encrypting the business messages, but people took it in a very different way, and they thought they will be not encrypting the private messages, and a lot of users migrated from WhatsApp to Signal just to have the privacy. So hence it is not really safe. The other question which I want you to think about is the masking of data is enough, right? So masking of data is enough. The point is probably not, because there are so many cases where the researchers are able to redo the data and come to actual data which was formed even with anonymizing and sanitization of the data. The famous case, I think, is the Netflix case, where Netflix released a data set which was about the movie ratings by different users. And in this case, the movies were marked as well as the users were marked as well. But there was University of Texas researchers were able to come back to the original data, but just by looking at IMDb and then trying to correlate between the Netflix data and the IMDb data, which is quite interesting. But at the same time, it also means that it is masking the data is not enough. So moving on to the next section, probably we need to talk about how the machine learning system works, and then we'll try to connect the privacy and machine learning into federated learning. So a typical machine learning system looks like this. We have the different devices, and we have the data collection that goes into a central server. So from the key point is all the data is going to a central server, which is the data collection part. And then we have model training happening, and finally an API is exposed, right? The endpoint is exposed as an API. And now if the devices when the devices want the predictions, they can connect to that API and get the output. Typical case is the Google Maps case, where you put location from A to B, and you will be able to see how much time it takes. So for that, Google is collecting all of your data, and then they are trying to build those models, which is basically telling you the estimate of the time. Now, the challenge with all of this is the data is being accessible by the data controller as well as the processor, and we don't really want that in our case, right? So we want the data to be with the data generator and not with anyone else, right? So that is a way to preserve the privacy. Now, this is a very cool slide, I feel. This is about introduction to federated learning. What we are talking about here are the different cases. Why do we need federated learning? What is federated learning? And a bit of applications that goes behind it. So why we need federated learning? I think we have touched upon that, but there are some more things that why it is needed. For example, there are several data regulations that are now in place, which restricts the usage of user data in some way. So we have the HIPAA guidelines, we have the GDPR, which is quite famous these days. And also the third point, which is also important, I think companies don't really want to reveal their data, even if it is for the betterment of the society, right? So a lot of times this happens because they want to protect their data, and they don't really want to give the data to anyone else, even if it is for, say, medical reasons or any other reasons. So in that case also, federated learning can play a very crucial role for the betterment of the society. We'll look into that. So what is federated learning? We have been talking so much about federated learnings, right? So federated learning is a technique where you are able to do the modeling, you are able to expose the API and everything, but without actually seeing the data, right? So how do you do that? Is that instead of sending the data to the central server, like we saw in the previous slide, now we are sending the model to the individual devices, right? So how do we do that? Is we have the different weights that basically define a model, a machine learning model, and we are trying to find out what is the change in weights from the individual devices by sending the model to the devices, right? And we'll look a bit more on that in the later part of the section. Also, let's look at a couple of applications, right? So some of the applications are the next word prediction. So in your Android phone, if you type messages, you'll be able to see that there is some recommendation of the next word. That is also an application of federated learning. There are some more applications like the predictive health suggestions, predictive car maintenance. So predictive car maintenance is again where it's about the different companies have different car manufacturers, right? So you may want to have a proper maintenance system for the users where they will be able to find out whether their car will be breaking down or not in the near future. But at the same time, you may want to have data from different manufacturing as companies as well. So here also federated learning can play a crucial role. Now let's look at the different levels of federated learning. So the different levels of federated learning is defined by the way you add in the privacy guarding, safeguarding. So the first thing is the federated learning basic. So in this case, we are just talking about the data is now with the devices and the model is sent to the devices, right? Um, Now, if we can somehow add in a bit of more cryptography into that and a bit of more encryption to the whole weights and everything, then we will reach to the second level of federated learning, which is adding the secret sharing and fixed precision encoding. We'll talk more on that. And the final one is if you really want to safeguard your privacy with everything, then you can add in differential privacy as well, which is basically adding a bit of noise to the data. Now let's look at federated learning basic. I think I've touched upon that, but this is how it looks like. So we have a central server, and the individual, the model is basically being sent to the individual devices, and then the updates are again going back to the central server, and finally the aggregation is happening in the central server, which is a intelligent and smart model. So here, all the data is being with the devices, and the model is being sent to the devices. Here is a bit of code which basically tells you how to do this. This is the code is written in PyShift and is also available in PyShift library tutorial. So here, what we are talking about is we have two devices, Elizabeth and Sam, and what we are, if you look at this section, then the model is training separately on device 1 and the model is training separately on device 2. And finally, all of the change in the weights are being sent to the central server. Let's call this as the central server. And here again, the averaging is happening. It can be any form of aggregation, depends on your use case. So the disadvantage to this is that it can be re-engineered. If someone looks at the change in weights, they can still come back and see that how the data looks like. So in this case, let's move on to the next level. How do you do that? Is you add encryption, right? So the way you add encryption is that there's a very famous secret sharing technique, additive secret sharing. So in this, what is happening is that you're trying to encrypt the weights itself, so that even if someone sees the weights, they are not able to re-engineer to reach to the data. Now, the advantage of this is you want something which is encrypted, and also at the same time you can do aggregation on it. So for that, additive secret sharing is being used, and fixed precision encoding is just a layer on top, just to make sure that the additive secret sharing is working on the floating point numbers. Again, in terms of code, it looks pretty simple. Actually, in PyShift, it is quite easy to do. We have this function called the dot fixed precision, which basically allows you to incorporate the encryption. This is all good actually. So far in level 2, if you have level 2, this is all working fine. But if you want extra level of security, you can add in differential privacy. So differential privacy is basically adding a bit of noise to the data itself, so that even if someone at somehow reaches to the data, but they will still not be able to find out the complete data, right? So they will not be able to do that. How it works is that I have this example in the bottom right corner, which I think makes it very clear. So we have two images, and if you look at the top first image, one image is changed, right? So let's call that a bit of noise to the data itself, and this is what I was talking about in terms of differential privacy. So in differential privacy, we have two kinds of noise, Laplacian and Gaussian noise, and it is basically measured by a metric called epsilon. So as you as you already probably know that if we add more noise, we are where so here the privacy is increasing, but at the same time our accuracy we are trading off, right? So this is something which needs to be we need to keep in mind. Lastly, let's look at the benefits and challenges of federated learning. So there are a lot of benefits, right? So first thing is definitely we are ensuring privacy, because the data is with the device where it is being generated, so nowhere else. The second key thing is lower latency, because the model is now in the individual devices, so there's lower latency, and the data is not being sent to the central server, so there you are saving time, right? The third thing is it is smarter models, right? So you are able to access the data directly as soon as it is generated, right? So it's not something that someone is working on the data and massaging the data, manipulating data, and then the model is being built, right? So this is theoretically this should be the smart model. And the last point is the less power consumption. This is from the person who is from the central server's point of view, because we are distributing the model itself. All the computation are being happening in the individual devices rather than the central server, so hence we have less power consumption. Now let's look at some of the challenges. The first challenge is expensive communication, right? So we have so much of communication happening here. It can be really expensive between the devices and central server. The second point is lesser control. So for the person who is actually creating all this system, he or she probably will not have that much of control, because everything is encrypted, and even data is not viewable, model out weights are not viewable, nothing is available, right? The third point is fewer frameworks. It's kind of, so federated learning is kind of new to the market. There's only a couple of frameworks which are really famous. One is PyShift, the other one is TensorFlow encrypted. Both of them are really good, but there's only two as of now. The last point is the statistical heterogeneity. This point basically means that individual devices will have their own noise in terms of the model building, right? So for example, when you type messages, you type in a specific way, right? So for example, you may write, instead of lol, you may use smiley, where someone else can use lol, right? So in that case, what happens that if I have millions of devices and there are some biases happening within the devices, then the whole model goes to a biased output state, right? So that is what the statistical heterogeneity means. So far we have spoken about federated learning and the challenges and benefits. Now let's move on to the next section, which is about fair clustering, and Sharmistha is going to be talking about that. Over to you, Sharmistha.
Thank you, Subarna, for the wonderful insights and giving an introduction of federated learning, its benefits and challenges. Now, I'm going to talk about fair clustering in federated learning, and that's one of the main aspects of ethical AI in federated models. So in this section, we will mostly concentrate on incorporating AI ethics in the required use cases that you may want to do when you go back to your organization, so that you are able to build fair ML models and define the appropriate metrics, what is used to judge that the model is fair and private. And along with that, when we talk about ethics and interpretability, we will also see an architecture, how you can fit the entire model. Now, what are the problems with federated learning out with clustering, and why we talk about clustering? So clustering is one of the mechanisms how we incorporate fairness in federated models. So basic problem lies in federated learning. Non-independent and identically distributed data actually are found to degrade the performance of machine learning models. And that's why researchers have come up with combining fairness objectives with privacy. And that's, again, another challenge and is a new area of research, like how do we combine fairness, privacy, so that the computation cost is also less on the devices. So what are the approaches that we have followed? So different groups of users might have their own objectives, data aggregation, so that all the data are from different clusters are aggregated, from all the different sets of devices, and which devices behave similarly are aggregated and represented through proper clusters. How do we ensure that the clustered membership of different incomes are proportionally represented? And how do we do that in a distributed framework so that we are able to deploy in a production setup? And while we do that, our objective is to attain accuracy of performance as close as to the conventional federated model, so that we are not degrading performance, and also we can leverage the best clustering objective for each of the clusters. Here you can see that you can predict disease mortality, ICU conditions from different patients coming from three different hospitals. And each of these hospitals may have, say, one or two different clusters. And we go against the conventional assumption that all the data from coming, all the devices are equivalently distributed or have similar machine learning or similar statistical distributions. So we try to correct that assumption and instead use clusters of devices and put the devices in those clusters which behave similarly. And our objective at the end of the day is not to ensure only fairness or privacy or security, but how do we make the clusters dynamic so that the clusters can coalesce, means the clusters can unite, or the clusters, if needed, can be broken into different clusters, and trying to do that in a federated environment in a decentralized manner. Now, what are the risks? What are the risks with federated learning with clustering? There are data privacy breach, there are fixed shape of clusters, as we have talked about, and even the client data coming from different differences may vary with their timing and characteristics. And it is the non-adaptive nature of the clusters. So what are the solutions for that? So the solutions we have tried to incorporate is including data compression techniques through autoencoder, so dynamic cluster adaptation while preserving privacy, and also merging the different clusters, as we have talked about, so that the clusters have an optimal select score. That is one of the main characteristics of measuring clustering. And all we try to do that, we have to do it in a multitask environment in federated learning, so that there are no adversaries who can disturb or break the privacy of the entire settings. So what are the different parameters or metrics that you would like to monitor? So one of them is the privacy budget, so that it tries to give a measurement that how private is the data. If we remove one single record from a data set, as Subarna has talked about, there should not be any output or the model outcome should not be distinguishable from the two results. So one data record is removed and the model outcomes from the two different machine learning models should be similar. So there is no way the attacker could distinguish or go back to the original data. And we also have sensitivity. How do we measure sensitivity? It is the amount of noise that we add, and it is measured by the one norm of a distance between the two data sets that differ in a single element that we have seen in differential privacy, what we have. So now, fairness, what are the metrics that we need to measure for fairness? So the protected and the non-protected loss. So for protected loss or non-protected loss, we take into different distance parameters like Euclidean distance or Manhattan distance between centralized and protected or non-protected attributes. Now, the most important thing is lambda. As Subarna has talked about, that we have to make a compromise or a trade-off between the actual accuracy as well as the fairness or privacy metrics. So how do we control the trade-off between the clustering objective and the fairness penalty? What are the when we do that, what are the conventional model metrics that we should also take into consideration? These are accuracy, precision, recall, and F1 score. Now let's look at or reiterate that what we have learned from the beginning. So first we have seen how vanilla federated learning works. So it's like nothing like a central server pushes a basic model to the devices. Devices have their own local data. They try to learn and send it back to the central servers. We have sending weights. We can also add encrypted bits, then we move into the second phase, that is encryption and DP-enabled federated learning. So here we see homomorphic encryption, encrypting the weights, and on top of it, we can also add privacy at the application level of the individual devices. And then ultimately the model gets pushed to the central server, and central server does the averaging. Then after that comes the third phase, that is the encryption and DP-enabled clustered federated learning. And what happens during this phase is that all the previous two phases stays, the second phase rather, the stays, and instead on top of it, we add clusters where similar devices are grouped into different clusters. And once a model is trained per cluster with the differential privacy, and that model per cluster is sent to the central server, and the central server averages it and pushes the model to the different clusters. So that the objective remains that every demographic group, the minorities, say the black versus the white, everyone is proportionally represented in each cluster. And that's what we are trying to achieve through the clustering assignment or like the objective function. There are cluster perturbation techniques, like when we talk about differential privacy, we do add noise. And ultimately, we do have to control the trade-off between privacy and fairness or accuracy. Now, how do we do in a distributed setup? So there may be a problem of scalability because a lot of points are there. So what is the objective we try to achieve? We try a small weighted point set for such that for any K subset, we are trying to optimize a small subset of data from the whole data set and with a fairness constraint. And then we try to apply that with cluster perturbation techniques, fairness, and then try to deploy that with in a larger setup to that ensure scalability. And repeatedly, we can use that and see where the cluster performance is maximum and us to accelerate the computation time, save the storage space of the devices, as well as there are different distributions that we can compare. That first iteration we have that, second iteration we have that. How we compare that? That's the Kullback-Leibert fairness term that we can use in achieving that. So we have talked about this example. I've just put it here. You can go through that in the appendix, and later on, if you can get in touch with us, like how do we, there's a paper on it, variational fair clustering. So we have taken IoT data set for male and female and tried to achieve the clustering results at different values of the fairness objective. Now, how do we deploy the federated learning in IoT edge networks so that the processing happens at different components. So here you see an automobile scenario where we can want to apply federated learning with GPS coordinates, be it train transportation or electric vehicles. And when we try to do that, we see that the finest granular feature like GPS, we are able to add noise and get back the actual location. So we have to be very conscious the way we add the noise, because if a person is walking around say a city in a road, if we add a wrong noise, 0.01 seconds of north or east may end up into like 10 meters ahead, and it may end up in a pool. So we have to be very careful how, when we talk about ethics, it helps us to comply by data contracts, compliance, and ethics. And there is also a structure or a architecture available with federated localization framework, which uses clustering. So at the end of the day, we are having better performance with fairness, privacy. We are building robust models which have fine-grained features, as well as we are building data. We have moved from building models with siloed data to non-independent and identically distributed data. So that's the objective. And you can also go through that federated localization framework, how it works. Now, we have talked about clustering, fairness, ethics, so many things. And one of the primary applications of this is the healthcare system. So here we get data from different industrial IoT applications, and we try to train the data with differential privacy as well as clustering. And what is the need? Here you can see that we have a representation saying that Black Americans are more likely to have prostate cancer. So how do we audit it, or how do we say that the result is verifiable? So unless and until we have sufficient data for the minorities or Black people, we cannot say that. And that's the objective I have talked about, or bringing the concept of clustered federated learning in distributed differential private system, so that non-discriminative predictors for protected groups with race or gender are proportionally represented with equivalent error rates for either minority or majority. And when we think about doing that in a distributed architecture, we have three layers primarily. One is the client. So the client is able to send the models, the clusters are able to send the models to the edge. So edge offloads part of the task from the client, so that it is helping the clients not to process heavy tasks. And ultimately, from the edge, it gets to the central server, who does the aggregation and sends back the local updates to the edges as well as the client. So that's the thing here. If you see this architecture on which we have put it in a horizontal shape, like the client is more engaged with the feature extraction, feature distillation, what are the features which are important, followed by noising techniques, where it does add feature perturbation. And where the edge networks are more concerned about the heavy processing. If the client is doing the conventional layers feature extraction, the edge is concerned with the gradient loss and stochastic gradients, so that through deep neural networks, so that the optimization is achieved, and that's pushed back to the server, and the server learns and averages all this and pushes it back to the client at the edge, so the task gets distributed. And as we have seen that we are now into a totally new phase where we have security, multi-party secured encryption, followed by encryption with fixed precision encoding, cluster sensitive data, where we ensure the clusters are fair with proper select score, differential privacy, and that model is ultimately pushed from the Google server. Now, we have seen so many things, so hope it helps you. And when you go back, you can apply those concepts. You have learned about federated learning basic concepts and we have gone into deep dive into federated learning evolution phases and how to select which use case and which application will cater to which use case. Then we have seen also the architecture and the deployment systems, that how you can incorporate privacy, security, and fairness. So there are a lot of resources already mentioned in the PPT, and if you want to get in touch with Subarna and me, and also we can tweet us. Before we close the session, just the final summary that how do you build a complete federated model? So whether you build a private, fair, or a full ethical system and with interpretability in it, you are in a situation that you should be able to deploy that model either on-premise, native cloud, or in a hybrid setup. And it's not only about building privacy and fairness into the ML part of it, but you should also have a fairly secured big data pipeline and a fair enough API privacy built into the architecture. Otherwise, there will be adversarial attacks that can compromise your systems. And when we address federated learning, we are addressing privacy issues with centralized data, so in a decentralized manner. And this use case can also largely be taken up with social recommendation systems, GPS, trajectory data, and sensitive health data. Now, when we build the systems, we have to be aware that the setup is scalable and it does have auto-correction enabled security and ethical ML framework built into it, so that we are evolving every day as we learn with new data. So if you see the cycle, the main characteristics of the model of the setup should be identify the use cases, apply it, measure the metrics which we have talked about, scale and improve, all done in a scalable agile way. And we have the appendix and demo some of the research results here. You can go to it and later contact us saying how did we do this and how did we apply this. The GitHub link will be shared in the chat. Thank you.